We've learned a lot about the behavior of gases using the partition function, the translational partition function. I want to take this in a similar step, but with a little bit different twist to it. All right, we noticed that in the partition function, we were using a quantity like e to the minus ej over kbt as a way of determining the relative importance of different states. Well, Maxwell took this idea a little bit further in looking at the velocity distribution of gases, and he proposed that we might associate a probability of finding a gas in a certain velocity based on a very similar sort of number, a very similar sort of expression, where we would take the kinetic energy of the gases, divide by kBt, and maybe multiply by a normalization constant that would then make this into a probability density. Now in this case, we've got a continuous parameter, the velocity of these gases, that we're using to measure the variation of probability. So what we have in effect is a continuous probability distribution. Now these are a little bit different from the discrete probability distributions that we're more familiar with, and let me explain briefly what the difference is. Let's suppose I have a variable x, and I know that there's a probability that depends on that variable, and I can graph that probability density as some kind of smooth function of that variable. All right. Now, the points on this curve are not probabilities themselves. In fact, the probability is going to be the portion or the area or the fraction of the area underneath this curve relative to the entire curve. That represents a probability of being in that area. So let me step back a second. Let's suppose we have taken the area under this curve and set it equal to 1. I shouldn't say almost, it is equal to 1 because we have normalized the curve. And that's in fact what we're going to do with this constant n that's out front here. The points themselves aren't probabilities, but relative areas inside this curve are probabilities. So if we're interested in the probability around a certain value of x, we might take a small sliver around that value, we'll call it dx, and evaluate what the area of this sliver is going to be relative to the entire curve. So in effect, the probability is related to the height of this sliver times the width of the sliver, which is px dx. So this is the thing that represents a probability in a continuous probability distribution. All right, now when we're dealing with something like gases, and we're dealing with particles that are moving in 3 dimensions, they not only have a magnitude of velocity, but they have a direction as well. So we're going to need to care about the x, y, and z components of velocity, but we can relate them to this quantity v, which I'll call the magnitude of the velocity. We can relate them by using spherical polar coordinates. So for example, I could say that the x component of the velocity is just going to be the magnitude of the velocity times sine theta cosine phi. And I could say that the y component is going to be the magnitude times sine theta sine phi. And the z component would be the magnitude times cosine theta. So basically all we've done is we've set up spherical polar coordinates, but we're set them up for velocity components. Just like spherical polar coordinates for position, we have a volume element here that's going to be given by the velocity magnitude squared times cosine theta, dv, d theta, d phi. And it's important that we're going to use this in any sort of calculation that we're going to do with a function that only depends upon the magnitude of velocity. So let me basically describe what that means. Let's suppose that I'm interested in evaluating some function of v, but it doesn't have any dependence on theta or phi. If I do this over 3-dimensional space, I still have to include parts that relate to theta and phi. So I'm going to have these kinds of integrals, but remember I have a component of theta in the volume element, so I have this. But these are the only parts that will contain dependence upon theta and phi. The velocity part has a component here, v squared, times whatever function it is that I'm evaluating, dv. All right, but the trick here is that since there's no other place where phi and theta appear, I can do these integrals in advance. This integral is easy to do, it's just 2 pi. And this integral is also easy to do, and it just has the value 2. So it means that whenever I'm evaluating an integral like this, and I want it to be for a three-dimensional distribution of some sort, and it's isotropic, that is to say it doesn't depend on its direction, then I'm just going to have a factor of 4 pi that comes from these two pieces times the integral over v, which is going to be v squared f of v dv. So this is the integral that I will need to evaluate, and the 4 pi is just the factor that I would get from it being distributed in any direction in space. Now we can use an integral like this to determine what this normalization constant is for this probability density. How do we do that? Well, what we want to do is set up a similar integral, 0 to pi d phi, 0 to pi of cosine theta d theta, and now we're going to have an integral from 0 to infinity of v squared times this function of p, which is n times e to the minus mv squared over 2 kt dv. Now this part here is going to give us this 4 pi once again, as it always will, and I can easily evaluate this part because it's a tabulated integral. I might be able to do it if I'm clever enough anyway, but I won't belabor the point. I'll simply say that the result that this gives us is that the constant n is going to be equal to m over 2 pi kbt raised to the 3 halves. Now I may want to include that 4 pi in this if I wish, and then I'm always talking about an isotropic problem, but sometimes you won't see that combined with the n. Nevertheless, what it means is that since the property of relevance is really this probability density times an increment in velocity, what I'm really interested in is this, p of v dv. And now I have an expression for p of v because I know what n is. It's just going to be 4 pi times this constant that we've evaluated by normalizing the curve times v squared, then this functional form for p, e to the minus mv squared over 2 kbt dv. So this thing here is the important result that we want to get out of this. This is something called the Maxwell-Boltzmann velocity distribution. And it is the general velocity distribution that we find for all velocities of gases at thermal equilibrium. Now, how would we use this? Well, let's suppose that we're interested in finding the average speed. So the average speed is just going to be v. So what we would do is we would want to take our integration over all velocities, take the function that we're interested in evaluating, which is v, and then we would multiply it by this Maxwell-Boltzmann distribution. So we'd have 4 pi m over 2 kbt, 2 pi kbt, all of this raised to the 3 halves, v squared e to the minus mv squared over 2 kbt dv. All right, this would be how we would evaluate an average velocity for this. And just in case you're interested, you can do this integral, and I invite you to do it. I hope you will. It's equal to 8 kbt over pi times m. All right, so you can see it's not precisely the sort of thing that we got before for the average kinetic energy, but this would be the average speed of particles at temperature T, and this is the prescription that one would use to evaluate that.